All right, good people. Let's look at our second example. We're doing improper integrals. And here we have an improper integral. I know this because I see there's infinite behavior at the end of the limit, top limit of integration. So here's the graph, y equals 1 over x. Again, we're looking to find the area under the curve starting at 1 and then shading all the way to the right, which looks very, very similar to the picture we had in number 1. So we're going to follow the same process. I'm going to set this equal to the limit as t approaches infinity of the integral from 1 to t of 1 over x dx. So I got to show that I'm understanding we can't really use infinity as a value because it's not. And so I'm going to use the limit to get closer and closer to infinity. What does that mean? Well, my numbers are going to get bigger and bigger and bigger. They're going to increase without bound. But I can't do it just by plugging in infinity because infinity is not a number. So I'm using the limit to help me out. All right, so I'm going to take the antiderivative of 1 over x. Well, the antiderivative of 1 over x is the natural log of the absolute value of x. But I'm taking the limit of that. And not only am I taking the limit of that, I'm taking the limit of that after I evaluate that at t and at 1. So I have to plug in the t and I have to plug in the 1. Can I skip this step and go directly to this one? Probably. And I would get the natural log of t minus the natural log of 1. Well, the natural log of 1 is 0. So that's nice. This kind of goes away. And so now I only need to deal with the limit as t approaches infinity of the natural log of t. Now, if you remember what the natural log function looks like, the natural log function is a slow growth function. So remember, exponentials go like that. They get big really fast. Logarithms go like this. They're getting big, but they're getting big slowly. But if I'm going to infinity, it really doesn't matter. If I take the natural log of 1,000, the natural log of 1,000,000, the natural log of 1,000,000,000,000, my numbers are getting bigger and bigger and bigger. Although slow, they are approaching infinity. So this limit does not exist because it grows without bound. So therefore, this area here never has a finite answer. It goes on forever. It goes to infinity. And so I can say that this improper interval diverges. And so we can do a couple of these and we realize that an integral that's set up in this format, we call it a p integral. P integral because it's 1 over x to the p. It follows that pattern. If you notice, number 1 was 1 over x to the 4th. Number 2 was 1 over x to the 1. So whenever I have that layout of a function, 1 over x to the p, we know that it's going to converge if p is greater than 1, but it's going to diverge if p is less than or equal to 1. That's what